is you are going to see three graphs that pop up. So if you ever see a question or an FRQ in which three graphs are presented to you, this is more than likely giving you information of if the chemical reaction as to what order it is. Just by looking at the three graphs, you can figure that out. The three graphs, and I'm going to change my color of my pen here, is concentration of whatever the reactant is versus time. The natural log, ln, the natural log of the concentration. So simply taking the concentration values and taking the natural log of them and plotting them versus time, and then the inverse of the concentration versus time. From these three graphs, only one of the graphs will be linear. And whichever graph is linear, that tells you the order of the reaction. Now, the concentration versus time graph and the ln concentration versus time graph, these guys will always be going down because a reactant decreases over time, and therefore the concentration goes down over time. But when you take the inverse of that concentration, since the reactant concentration is going down, if you take the inverse of that, that means it's going to show an increase, and therefore this is going to be the only graph that you will see going up versus time. And that's because it's the inverse of the concentration. From the three graphs, only one will be linear. And you can see that in this case, the one that is linear is right here. So if you have a 0th order reaction, you are going to see the linear plot be the concentration versus time graph. So if on the national exam you're given three graphs and the one that's linear is the concentration versus time graph, what that tells you is that it's 0th order. Why? Why is it 0th order? Because the concentration of the reactant, does not affect the rate of the reaction. Since the slope of the line is perfectly linear, that means the slope, which is the rate of the reaction, is constant. It has a constant slope, that's why it's a straight line. And therefore, even though the concentration of this is changing, it's going down, the rate of the reaction is not changing from that change in concentration. So this is how you can justify it. If they ask, how do you know what the order of the reactant is? You would say that it's 0th order because the concentration versus time graph is linear, and therefore the concentration of it does not affect the rate of the chemical equation because it's a linear plot. The other two graphs, as you can see, will have curved lines. Okay? So if you have a 0th order reactant, 0th order reactant, the concentration versus time graph for that reactant will give you a linear plot. What happens if it's not 0th order? Okay, now let's look at B. Let's say that it's 1st order. Now, if it's 1st order, the concentration versus time graph will not be linear because since it is affected by the concentration of the substance, you will notice that the slope of this line keeps getting shallower and shallower. The rate of the reaction is slowing down, as we've seen from the last couple of lectures. And because the rate is changing, the slope of the line is changing, concentration does affect the rate of the chemical equation. Now we can see that the linear plot is the ln, the natural log of the concentrations versus time. Okay? So now if this graph is linear, I know that it's 1st order. So we're proving if it's 1st order by looking at this concentration. So therefore, if they ask you to justify, you would say that the natural log of the concentration of the reactant versus time shows a linear plot. And whenever the natural log of the concentration versus time shows a linear plot, that indicates that it's 1st order. Again, only one of the three graphs will be linear. In this case, these two graphs are not, and therefore this would indicate a 1st order reactant. Lastly, if it's 2nd order, the concentration versus time graph, again, the slope is changing, which means concentration does affect the rate of the reaction. The natural log also is such, and therefore the equation that's linear. In this case, it goes up because, again, the concentration of the reactant is decreasing, so the inverse of that will show an increase. If this is the linear plot, then it's second order. So now, again, if we were asked to justify it, we would say that since the 1 over the concentration versus time plot is linear, therefore, okay, it's a second order reactant. Okay, now because I know that it's second order, I can immediately then, they might ask another question on the FRQ, it could be, write the rate law, therefore, of this chemical reaction. And you would write the word rate equals little k times the concentration of the reactant, I'm just going to say A, squared. So from that, because I know it's second order, if it were to be C's case, I can now write the rate law of the reaction because I know it's second order. Same thing could be first order or 0th order. So again, one of the 3 graphs will be linear based on which one it is. That'll tell you what order the reactant is, and therefore now I can write the rate law for it. That's the key conceptual understanding of today's lecture. For the same reactant, so same products over here, but you'd see pressures if it's a gas. Okay, so don't let that shock you if you don't see concentration values, but you see pressure values, which is always, again, interchangeable if it is a... Well, look at these graphs. Once I identify what order it is, the slope of any of these graphs, the slope will give me the rate constant of it as long as it's positive. So if you get a negative value, just make it positive. The slope of the line gives me the rate constant. They'll be given 3 graphs. One of the plots will be linear. Whichever one is linear will give you or tell you what order it is. You can write the rate law from that order, or you might be asked to figure out some other type of variable in those chemical reactions. Okay? I strongly recommend that you do the practice problems. If you have questions, please seek me out. This tends to be the hardest concept in this entire unit for students to kind of grasp. So if you do have questions, please seek me out. I'd be glad to kind of go through a couple extra problems with you, and usually when we do that, it tends to click a lot more for some students. Again, I appreciate you listening to this lecture. All right, today's lecture is going to be on something that is called the integrated rate law. And the integrated rate law is where we utilize calculus as a way to figure out linear equations that we can utilize to solve for different variables in these chemical kinetic problems. Up at here is a very important table. It's one that's not on the national exam, but does a really good job of highlighting all the key points that we're going to talk about today. And right here is the last lecture focused on how to write a rate law. To write a rate law for a reaction, you write the word rate, and then you set an equal sign, and then little k is called the rate constant. And that gets multiplied by the orders, the concentrations of the reactants, increased to whatever order they are. And again, the order is what power is on the concentration of that reactant. If you have a 0th order reaction, 0th order, the rate law for that is rate equals k. Since the concentration of none of the reactants affects the rate of the reaction, you literally have the rate equals the rate constant. This is extremely rare, and often you will not see it in real life very much. Now, it doesn't necessarily mean it won't pop up in the national exam, but you have to understand is that's what you get for the rate law for a 0th order reactant. If it's first order, which is the most common, you get rate equals rate constant times the concentration, again brackets around the reactant, whatever it is, raised to the 1 power. Now you don't necessarily put the 1 there, but it is there. Okay, so that 1, the power on that concentration of A is called the order. And what that means is one molecule of A collides with either another molecule or the walls of the container, causing the chemical reaction to occur. A second order would be where we have rate equals K times A squared. So now there's 2 molecules of A involved in the step that involves the or controls the chemical kinetics, how quickly the reaction rate occurs. Now, one thing that you might see in the national exam that's very common, okay? All right, couple other things. From the linear line, we are now going to develop, because it's a linear line, we are going to get what is a y equals mx plus b relationship. When we get the linear plot, because it's a line, we get y equals mx plus b. And that y and mx and b are looking at different variables, okay? And we can now study those, and I'll look at those in a few seconds here. The linear plot, as we already talked about, is going to be which graph is the linear one. If it's the concentration versus time graph, it's zeroth order. If it's ln, it's first. If it's the inverse, it's second order. And lastly, something about half-life. The half-life is the amount of time it takes for half of the reactant to disappear. We'll talk more about this in the next lecture, but we've talked about half-lives before when it comes to the decay of isotopes that are radioactive, but this also applies now to chemical reactions in which at what time does it take for half of the reactant to be totally consumed. All right, so let's take a little bit more further in-depth look at each of these orders. If you have a first order reaction, which is the most common in the national exam, if you look at the kinetic section of the chem helper, the green reference sheet that I gave you. Okay? In the kinetic sections, there are 3 equations. The first equation on the national exam is right here, okay? Which is the natural log of the concentration of A at a specific moment in time minus ln, the natural log of concentration of A0. A0 is the concentration of the reactant at time equals 0 seconds. So, what is the concentration of a reactant when the time of the reaction is at 0? Well, the reactant hasn't started reacting yet. Therefore, A sub naught really is the initial concentration. So, A sub 0 is the initial concentration of the reactant. Okay? The natural log A sub t is what is the concentration of it after a certain moment of time. Again, as the reaction proceeds, the concentration does go down over time, and therefore it's going to become smaller and smaller. Okay? K again is the rate constant, and T is the time interval. The concentration of A of T, whatever the T is, so let's say the T is 10 seconds. What A sub T would be is what is the concentration of the reactant A at 10 seconds. Not at 0 seconds now, but 10 seconds. So the time used in this equation correlates to what the concentration of it is at that exact moment in time. Okay? So if I were to graph a concentration versus time graph of a first order reactant, that graph would not create a linear line, as you can see here. It's curved. Graphing the natural log of the concentration versus time graph will give me a linear plot, as we can see here. Okay? Now again, because it's a line, we get y equals mx plus b. Well, what is the slope of the line? The m. The slope of the line has been found to be k, the rate constant. So the slope of the line is the rate constant of the chemical reaction. The y-intercept is going to be, for the first order here, is going to be the concentration of the reactant at time equals 0, because it's the y-intercept. But in this case, since it's a first order reactant, it's not the concentration, but the ln of the concentration. So the natural log of the inverse of the concentration would give me the initial concentration of the substance. Okay? Now remember, that gives me the natural log of the inverse concentration. How do I get rid of that? Is if I were to take little e of that number. If I were to take the little e of the natural log of the A value, they cancel, and that would tell me the initial concentration of the substance. Okay. All right. Now you'll notice that instead of being concentration here, we notice pressure. If it is a gas, we could see it be a pressure versus time graph or a natural log of the pressure versus time graph. It necessarily doesn't have to be concentration if it's a gas. So again, be careful. It could either be concentration or pressure, partial pressure of the substance if it's a mixture. So, but again, you'll see pressure, natural log of the pressure, and inverse of the pressure. They're gaseous substance. Okay? Now, once we know what order it is, we now can use the slope of that line to be able to answer a question. So for example here, it says a chemical reactant is known to be first order. Right away they tell us that it's first order. If the initial concentration of A is 0.075 molar and the rate constant is this, what would the concentration of it be after 1 minute? All right, because it is first order, I immediately know on the green sheet that the natural log equation, is going to give me, or is an equation I can utilize to solve this equation. All right? So they want to know what the concentration would be after 1 minute, which would be the concentration of it after a certain time interval. The initial concentration was given to us as being 0.075 molar equals negative K. K is the rate constant. And the time interval is 1 minute. Now, right away I notice an issue, and hopefully you did too. This says 1 minute, but the rate constant is in seconds. We have to make sure that the units match so they properly cancel. So 1 minute, we should all know, is 60 seconds. So I'm not going to plug in 1, but I got to be aware of the units so that the units will cancel out. All right, so now if I go ahead and grab my calculator. All right, so I'm going to go ahead and add the natural log of 0.075 over to this side. So now I'm going to take the natural log of 0.075 and then subtract 2.2 times 60. Make sure we multiply the rate constant times the seconds first. So again, the natural log of 0.075 minus 2.2 to negative 3 times 60. So now the natural log of the substance would be equal to negative 2.72. Again, to get rid of a natural log, we have to use little e, which is always the second function of the variable. So if I take little e to negative 2.72, that is now going to give me the concentration of the reactant, in essence, at 60 seconds. So what is the concentration of A at 60 seconds? And it gives me 0.0657 molar. So the concentration is less, which it should be because the reactant, there should be less of it after a certain moment in time. So it has dropped. So the purpose of, once I identify what order the reactant is, I now can use the integrated rate law to be able to use it like a plug-and-chug chemical equation to figure out the concentration of the reactant at any moment in time. Or if I know the change in the concentrations, I can use it to figure out the rate constant because that'll be the slope of the line. Now be careful, when you do get the slope of the line, the slope will be negative. The rate constant, little k, can never be negative. So the slope of the line is really equal to not k, but negative k. You have to be aware that then just get rid of the negative sign because the rate constant can never be negative. All right, so that's how we look at first order reactants. Now what sheets is the zeroth order integrated rate law. It's not on there. They expect you to know that if it's a zeroth order reactant, that for the actual question, second order. If it's second order, now the natural log of the concentration of the substance, again, will not be a linear line, so I can't use it. What will be a linear plot will be the inverse of the concentration versus time. And again, this graph will be the only one that ever goes up. And because it goes up, the slope of this line will also equal the rate constant. But in this case, we don't have to worry about the negative because it is a positive slope. On your green sheet, this is the second equation given to you on the green sheet. So when you see the chemical kinetic section, the first equation shows the natural logarithms equals negative kT. The first equation in kinetics is the first order integrated rate law. The second equation is the second order reactant rate law, integrated rate law. So the nice thing there is if you just notice that the first one given is if it's first order and the second one given is second order, you know now the values. Now what's the third one? The third one is actually a half-life equation. It's a half-life for first order reactants, which we'll talk about on the next lecture. So there's a half-life equation. So what's not given to you on the graph that produces the linear plot for 0th orders is going to be concentration versus time. And therefore, you can get the 0th order integrated rate law if you need. I've never seen them ask that because, again, they didn't give that a chemical reaction. All right, now what do we have here? Again, the slope of the line is the rate constant, and the y-intercept is going to be the inverse of the initial concentration of the substance. Okay, so the 0th plot there, the y-intercept is going to be the inverse of the initial concentration. So if you know what the value is in this graph, I can just simply take the inverse of that, and that'll then give me the initial concentration of the substance. Okay? Again, if they tell you that it's second order, we know that the equation of the line is the second one in the chemical kinetics, and now I can plug and chug and figure out any of these different variables. I can figure out what the concentration of the substance will be at a certain time interval. I can figure out the rate constant. I can use this as a plug and chug equation because it's a linear equation, and I can use that now to be able to figure out some type of variable that I might be asked to solve for. Lastly, if it's 0th order, again, if it's 0th order, you're going to have a concentration versus time, or if it's a gas, pressure versus time. In either case, you are going to have a linear plot that develops whenever we have a 0th order graph. The y-intercept gives me the initial concentration of the reactant, or if it's a pressure, it would give me the partial pressure of the reactant, initial partial pressure. And the slope of the line gives me negative K. So to get the rate constant, we would just have to take the slope of the line and take the negative of it. The two negatives would cancel because the slope is negative, and that would give me a positive K. Okay, so again, the K, little k, can never be negative. All right, so the slope of all these lines. So whenever we look at these graphs, reaction. Okay, and therefore now I can utilize this equation. So again, this blue line shows a 0th order where it's straight. If it's first order, it's curved, as we already said. But if it's 0th order, the concentration at a specific moment in time will equal, well, I should take that off, minus the initial concentration of the substance equals negative kT. So the concentration at a specific time minus the initial concentration equals negative rate constant times the time interval. Those are the integrated rate law functions that we can now use as linear equations to solve for any specific variable. The initial concentration, the later concentration, the rate constant, or the time interval. Okay? Now, the homework problems that I have in this section, a lot of times read the question. If they identify right away what order it is, you can now look up the integrated rate law and use it to be able to plug and chug and solve some different variables. Or you might be simply asked a